Welcome to the first lecture of this course titled Mechanics of Composite Materials and Structures. Today in the first lecture, we will have a brief introduction to composites. So a composite material is a material which is produced by mixing two or more different materials to develop a new material with improved properties. So the main constituents of composites is reinforcement. So it can be fiber or particles, and that reinforcement is dispersed in a matrix. So a matrix can be resin, metal or ceramic. So depending on the number of constituents, a composite can be two-phase, three-phase or multi-phase. The properties of these composites are influenced by the constituent materials. So what reinforcement we choose, what matrix we choose, and then in what proportion we choose, and how is the fiber distributed, the reinforcement distributed, how they interact, the matrix and fiber, and also the geometry of the reinforcement. So this reinforcement can be spherical, cylindrical, they can have rectangular cross section, and they can be in platelet forms also. So that also affects the property of composites. Now here we'll see the classification of two-phase composite materials. First is fiber reinforced plastic composites. So these fiber reinforced polymer composites, this is something that we'll deal with in this course in more details. So here the matrix is epoxy, polyester, vinyl ester, or it can be thermoplastic. So there are two types of matrices. One is thermosetting, another is thermoplastic. We'll look into those as we progress. And then there are reinforcements, the fibers like glass fiber, carbon fiber, aramid fiber, and there can be natural fiber also. Then there is something called metal matrix composites. Again, as the name suggests, the matrix is metal, aluminum, magnesium, copper, titanium, and then the reinforcement can be boron, alumina, silicon carbide, and so on. Then there is something called ceramic matrix, ceramic composites. So ceramic composite means the ceramic is matrix, and there are ceramic materials has reinforcements. So for example, the silicon carbide, silicon nitride, alumina, they can be in the form of matrix as well as reinforcements. And then there is something called carbon-carbon composite. So a carbon composite means carbon matrix, and that has carbon reinforcement also. Now let us look into this metal matrix composite. So metal matrix composites has metal matrix, just like we discussed. These can be the metals, and then there are ceramic particles or fibers. So here if I compare with these properties of these metal matrices with those of a pure metal or unreinforced metal, then we can see that the metal matrix composite has better properties as compared to unreinforced metals. For example, they offer high thermal and electrical conductivity, and they resist moisture better, and then they can maintain performance over a wide range of temperature, and they can be engineered as hybrid composites also. Applications are diverse. So in aerospace field, they are used to make structural components. In satellite structures, it finds its use, compressor blades, jet engines, and so on. In the automotive field, brake rotors, pistons, drive shafts, structural parts. In the defense field also it has application, military vehicles, armor, high performance machinery. Similarly, it has application in other industries for carbide drilling, machinery components, in electronics, thermal management components, and there are various other uses also. Now ceramic matrix composites. So these are composed of ceramic fibers which is embedded in ceramic matrix, and they have high temperature resistance and stability. So that's why in high temperature applications, for example in high speed or supersonic or hypersonic vehicles, it finds its use. So they have high corrosion and chemical resistance at elevated temperature, but their compressive strength is somewhat lower because they have pores in between. Now it can be oxide based or non-oxide based. So at oxide based means both matrix and fiber are some kind of oxide. So oxide ceramics, the common oxides are alumina or mullite. So they have excellent chemical stability and corrosion resistance, and they are good electric insulator, they are easier to process as compared to non-oxide CMCs, ceramic metal composites, and they are commonly applied in aerospace heat shields. Like I told you that these vehicles suffer from significant heat due to aerodynamic heating, so for heat shields they are used, then electrical insulation and so on. And there are non-oxide based ceramic matrix composites. So these has either matrix or fiber, which is non-oxide compound. So the non-oxide compound can be silicon carbide, silicon nitride and so on, and they have high thermal conductivity, and they have excellent resistance to thermal shock, and they are mainly used for protective coating cases. So commonly used in turbine engine components, high temperature cutting tools, nuclear reactor components, etc. Now let us look into another application, that is carbon composite. So carbon composite has continuous or chopped carbon fiber in a carbon derived from pyrolyzed organic resins or pitch. So they have high strength to weight ratio, and they have excellent thermal resistance. So they can resist thermal up to 3000 degrees centigrade in non-oxiding environment, and their thermal expansion is quite low. So they have high dimensional stability in heat, and they have good thermal conductivity, and they are resistant to radiation. In aerospace applications, nose cones, rocket nozzle, heat shields, aircraft brake discs. In motorsports, high performance brake systems. In defense, they are used for missile components, re-entry vehicle structures. In the nuclear engineering, they are used for fusion nuclear reactor parts, and they have structural applications. And it is also used for high temperature furnace components. Here we can see comparison of the costs. So carbon matrices costs around more than 100 USD per kg. Ceramic matrix range from 20 to 100. Metal matrix 10 to 20 plus. Thermoplastics 4 to 60. And then there are these thermosetting resins, thermosetting matrices, and polyester is cheaper, vinyl ester is in between, epoxy is more costly. So we can see that carbon matrices are costlier as compared to the other composites, and if I go for these matrices, the polymer matrices, the cost is somewhat lower, and it has so because of this low cost and other advantages, this kind of composites which have this polymer matrix finds highest, most application. It has. So because of their low cost and other advantages, so this kind of composites where polymer matrices are used finds more applications as compared to other composites. This shows the economic growth trend of thermoplastics and setting polymers. So thermoplastic polymers is shown by the red part of this bar, and thermosetting is shown by the blue part of this bar. So we can see that the use of thermosetting is more. However, the use of thermoplastic resins is also, or the thermoplastic matrices is also increasing in a rapid way. So again, we have seen that there are these 4 broad categories of composites, and in this there is possibility that the matrix is these which are thermosetting and these which are thermoplastic, and we have seen their comparison. Now let us go to fiber reinforced plastic composites, which is this course about. So it consists of polymer matrix. Now this matrix in the original, before fabrication, this matrix that we get is in a liquid form, and we call it resin, and then this resin is hardened, and it's in a position to hold all the fibers, and then that's the solidified composite that we get. So when we see resin, it's basically the matrix material. So it consists of polymer matrix that is combined with fibrous reinforcement, and the reinforcement can be glass, carbon, aramid fibers, and there can be natural fibers also, depending on the application. and these are used extensively due to lower processing temperature and economic efficiency as compared to metal or ceramic matrix composites. Now, when we talk about fiber reinforced composites, there are two terms that we will be seeing very frequently. One is ply or lamina. So, a ply or lamina can be thought of one unit of the fiber matrix composition. So, in a ply or lamina, the matrix is there, and again that can be made of thermosetting or thermoplastic polymer. So, that is a polymer matrix, and that polymer matrix holds the fibers, and this is very thin sheet. So, that one thin piece is called one ply or one lamina. Now, within the ply, the fibers can have diverse orientations. It can be oriented in one direction like this. It can be oriented in multiple directions also, and also these directions, different plies can have different directions. So, one ply may be like this, another ply can have fiber orientation like this, and so on. And the fibers need not be continuous, it can be broken in chopped form also. Now, when we stack these plies up one over another, then we make a combination like this, and that is called a laminate. So, this is called a laminate. So, these are called ply or lamina, same thing, and this is called laminate. Now, within a laminate, the fibers can have, the plies can have different fiber orientations, and that is one of the benefits with composites. By changing these fiber orientations, we can design the composite to behave in different ways. So, that as a designer gives us immense design flexibility. So, again there can be two types of polymers. So, one is thermoset matrix. So, that is the matrix of thermoset polymers, and the composite that we get is called thermoset matrix composite. So, thermoset polymer is a type of polymer that irreversibly hardens when cured. So, there is something called curing of this polymer. So, initially the polymer or resin that we get is in liquid form, and after composite fabrication, the liquid gets hardened and it holds the composite, and we get a solidified composite. So, that process of hardening the polymer is called the curing, and during this actually there are lots of chemical phenomena that happens. There is something called cross linking that happens within the polymer. Now, for curing, we can sometimes add curing agents like hardener that helps in curing, and also we can change the external ambient conditions like temperature. We can cure it in a heated temperature that accelerates the curing. So, when it is cured, that means when it hardens, it hardens. Now, after that, if we again we cannot melt it or reshape by heating. So, that is the problem with this kind of polymers. So, the entire process of hardening is irreversible. We cannot get the liquid phase back. So, these are typically more brittle than thermoplastic, and they have higher thermal stability and they have high mechanical strength. Examples are epoxy, polyester, vinyl ester. Epoxy has higher mechanical properties, better mechanical properties than polyester or vinyl ester, but polyester, vinyl ester are better resistant to corrosion. So, that is why they find more application in marine field. Now, thermoplastic composite. Thermoplastic is on the other hand is reversible. So, even if it is hardened, it can again be melted or softened upon heating. So, this hardening and softening is a reversible phenomena here. Now, here the advantage is it has faster processing as compared to thermosets. So, if we want to produce in bulk, thermoplastic can be option depending on the other requirements. Then it has higher impact resistance than thermosets. It has infinite shelf life. So, we can store the resin for a long time, and they have better moisture resistance and than thermosets. So, there are various examples like nylon, polycarbonate, polypropylene, and so on. Now, the question is, what should I choose, thermoset or thermopolymers? so that depends on our requirements. First of all, if I need mechanical performance, if I need high stiffness and strength, thermoset is the choice. If I need high fracture toughness and impact resistance, thermoplastic is the choice. And if I need better fatigue resistance, then we can choose both. Both are good for fatigue. Now, depending on the other requirements, we have to finally choose one. As far as temperature condition is concerned, high service temperatures, thermoplastic. In the cryogenic temperature, both are good. And fatigue we have already discussed; it's not needed here. If I need to produce in bulk quantity, thermoplastic is better. So thermosets find application in aircraft main structures, wind turbine blades, and so on. On the other hand, thermoplastics find application in aircraft interior, automotive crash structures, etc. Now, depending on the fiber, I would say the fiber arrangement, there can be different types of composites. So there can be continuous fiber composites where the fibers are continuously arranged. So this kind of fiber arrangement gives more better mechanical properties, and also it exhibits anisotropic properties, because if the fibers oriented in this direction, we will get some property here, and in the perpendicular direction we will get different properties, and accordingly we can find out the properties in any other direction. So the properties become direction dependent, and that is a challenge for analysis but better for design, especially when we have diverse strength requirement in diverse directions, and also when we have other kind of requirements like shape adaptivity. We want to tailor some properties. In that case, the anisotropy helps us, and they are typically expensive and complex to manufacture than discontinuous type composites. So we are talking about continuous fibers here. Discontinuous type is just the other side of it. So there are short fiber composites, which is basically discontinuous type, which has discontinuous type fiber. So in short fiber composites, there are short fibers, and these fibers are randomly oriented in different directions in a composite. So fiber orientation can be random. It can have various fiber directions. Now, because of this random orientation in diverse directions, so in a bigger scale, when we see them, the properties are more or less isotropic, and they are less costly to manufacture, and they are suitable for high volume production, but their mechanical properties are inferior as compared to continuous fibers, and also they are not suitable for tailoring because we don't get the anisotropy here. Now we look into glass fiber. This is one of the fiber types. So there are glass, carbon, aramid, and there are natural fibers also. So we look into glass fiber first, and glass fiber can be of two types: S glass and E glass. S stands for strength. So this S glass fiber has higher tensile strength and modulus as compared to E glass, and they have superior temperature resistance and durability, but they are more expensive, and they have higher thermal stability than E glass, and they have good resistance to chemicals, especially moisture and corrosion. If we look at the composition, it is mainly made of aluminosilicate gels with high silica content and magnesium oxide. Typical composition looks like this. So it has silica 65%, 25% alumina, and 10% magnesium oxide. That is approximate. If I look at their property, then they can withstand temperature up to 700 degrees centigrade. Their tensile strength is around 4.5 GPa, and Young's modulus is around 86 to 90 GPa. And if we talk about density, density is around 2.5 gram per cc. Other properties like they have excellent fatigue resistance, excellent fatigue resistance, and also specific energy absorption. Specific energy absorption, that's around 40 to 60 joule per kg. Specific energy absorption means how much energy per unit mass can absorb. It's available in various forms. It can be available in roving forms. Roving means it's just like in bundle form like this, and then there are woven fabrics. So this is a woven fabric of glass fiber. So this is a fabric where fibers are there in both the directions, and this is a fabric where it is fiber is predominantly in one direction. There can be prepacked tapes also. Now prepack is something where the matrix is already there in the fiber, so the fibers are already impregnated with matrix. So we get fiber clothes like this, mats like this, which has already some matrix content. So if I just join different prepacks and cure them, we get the composite. And also we can get in chopped strand form also, that means chopped fiber. Applications are structural components, missile casings, body armor, ballistic protection, high performance turbine blades, high strength hulls, and high performance equipment. Now let us talk about E-glass fiber. E-glass fiber is most commonly used, and they have good electrical insulation properties. They have a high strength and they are of relatively low cost. They have moderate thermal resistance, and they have high electrical insulation, and they have good resistance to water and other chemicals. They are mainly made from alumino-borosilicate glass, so that has 52 to 56% silicon dioxide silica, 12 to 16% alumina, 5 to 10% calcium oxide, and 8 to 12% boron oxide. If I look at their properties, so they can withstand temperature up to 350 degrees centigrade, and they have tensile strength which is around 3.5 GPa, and Young's modulus that is around 72 to 76 GPa. Density is close to 2.55 gram per cc, and then they have good fatigue resistance and specific energy absorption generally lies between 30 to 50 kilojoule per kg. So there also the unit is 50, this kilojoule, not joule. They are available in various forms like continuous filaments, chopped strands, woven fabrics, mats and veils, prepacks, and also the applications include interior fairings, radomes of aircraft, panels, lip springs, bumpers of automotive, boat hulls and decks, FRP rivets, pipes, claddings, PCB insulation, enclosures, sport equipment, ladders, etc. Now let us talk about carbon fiber. Carbon fiber has very high strength to weight ratio, and it has good stiffness to weight ratio also. Now they have very low coefficient of thermal expansion, and they have I would say good fatigue resistance and creep resistance. They are more brittle and expensive than glass fiber, and they have moderately high thermal stability, Electrically they are conductive, poor resistance to oxidation at high temperature in air. So composition wise, it has more than 90% carbon. It's arranged in crystalline graphite like sheets. It can withstand temperature up to 300 degrees centigrade, tensile strength 3.5 to 6 GPa. Young's modulus is around 230 to 600 GPa. So we can see how much stiffness we are getting without adding much weight. And density, that's around 1.7 to 2 gram per cc, and it has good fatigue resistance, and specific energy absorption is that's around 10 to 30 kilojoule per kg. Now it's also available in various forms like continuous filaments, tows, yarns, and woven fabrics, prepex, and there can be braided forms also. So braided form is more complex form. So here it's more advanced than woven form. So there we get the composites arranged in various directions in various complex patterns, and there are chopped fiber also. And also nowadays we are talking about 3D woven composites also, so where the entire arrangement is in 3D, not in 2D. Then applications include aircraft wings, fuselage. So because of their very high stiffness to weight ratio and high strength to weight ratio, in this kind of strength critical applications it is used. Later on we will see in the big commercial aircraft, most of it is made by carbon fiber. In satellite structures for automotive monocoques and panels, racing boats, masts, it's used for retrofitting of bridges, columns. Then it has used in prosthetics and imaging equipments also. Now we'll talk about another type of fiber, that is aramid fiber. So this aramid fiber has very high energy absorption. So they are mainly used for ballistic applications like armors and armors. So here impact is a major concern. So it needs to absorb high amount of energy. It has low density. It has good resistance to organic solvents and fuels, but sensitive to acids and UV. It has high thermal stability. In fact, it can withstand up to 500 degrees centigrade in short term, and it can continuously withstand around 250 degrees centigrade. But the problem is that they do not bond easily with resins, so surface treatments are often required. So they are available mainly in two types: para-aramid, which is high tensile strength. Examples are Kevlar, Twaron, and there are something called meta-aramid, which is flame resistant. Example is Nomex. Now this, if we look at their properties, so tensile strength is around 3 to 4.1 GPa, and Young's modulus is 70 to 130 GPa. Density is 1.44 gram per cc, and they have excellent fatigue resistance, and they have excellent fatigue resistance. And if I compare all the fibers, aramid fiber has highest specific energy absorption. and this ranges from 50 to 80 kilojoule per kg. Again, it is available in various forms: roving, woven fiber, chopped, braided, non-woven mats, prepex, papers, and so on. Applications: mainly ballistic applications, helmet, body armor, bulletproof vests. In aerospace, lightweight structural panels, interior components. In automotive sector, racing seats, panels, and tires. In ropes and cables, because of their high strength and low stretch requirements, they are used. And also for protective clothing for firefighters and industrial gloves. Then there are something called natural fibers. So those are fibers which are obtained from natural resources. So it can come from plant kingdom or animal kingdom. Plant-based fibers are flax, hemp, jute, sisal, coir, coconut, kenaf, rami, banana, and bamboo. As far as animal-based fibers are concerned, examples can include wool, silk, alpaca, and they are low density, biodegradable, and low cost, and also they have low health risk, because handling other fibers like glass fiber is riskier, but that kind of risk is not here. But their mechanical properties are much inferior than the kind of fibers that we have discussed so far. Composition wise, if I look at the composition of a typical plant fiber, cellulose 60 to 80%, hemicellulose 5 to 20%, lignin 5 to 20%, and pectin and waxes in small amounts. Then if I look at the applications, door panels, dashboards, in the construction industry, insulation panels, roofing, partition boards, and there are applications in furniture and packaging, sport goods, surfboards, bicycles. So you can see that when the high strength and other mechanical properties are a concern, we don't go for carbon fibers. It's mainly for the low strength applications. Here let us see the comparison. If I look at the costs, natural fibers has the lowest cost, carbon fibers cost much more, aramid is almost the same as carbon fiber, glass fibers cost less, but S-glass fiber costs more, E-glass fiber costs less, and we have already looked into the applications. Now let us look into various advantages and disadvantages of composites. So these are advantages of composites in general, or I would say FRP composites. So in general, the advantages of FRP composites are listed here. These have high strength to weight ratio, we have already seen it. So without adding too much of weight, we can increase the strength if I go for composites. This has good corrosion resistance, and it gives us immense design flexibility. So it can be molded into various shapes. So we can go for in many cases the shape itself becomes a part of a good design, and then composites helps us because it can be molded into various complex shapes. And also we have large design parameters. We have seen that we can orient fibers in different directions at different plies, and that gives us immense flexibility as a designer. And because of these design flexibilities, we can do various tailorings. We can go for shape adaptive design, aeroelastic tailoring, and so on. They have very good fatigue resistance, and because of their low temperature coefficient, they give good dimensional stability. We will see the applications of all these, composites, and where these kind of advantageous features help us in the third week. And they have good electrical insulation and conductivity. In harsh environments, they have better durability, and the composites have better damping because of their resins, so it can dissipate energy faster. That's why in damping critical applications also composites are used. In vibration, where we expect a lot of vibration, we can see the use of composites. There are some disadvantages. First, high initial cost, raw material and fabrication process can be expensive. It is difficult to repair. Composites are prone to various defects, and many times these defects lies inside. So if I have a composite laminate like this, it is made of different layers. So many times we will get defects in between two layers. So the two layers detach from each other, we call it delamination. And apart from that, there are other defects like matrix cracking, fiber breakage, and those defects are difficult to repair, especially the defects appear in at the inner side of the composite, and they have poor fire resistance, especially thermoset matrices. It burns and releases toxic gas. It is difficult to recycle, and the failure mode is often brittle, so it does not give much warning before failure, and quality control is an issue. So while fabricating, we need to do good quality control so that there is uniform mixing of resin. We don't get too much of void, fiber misalignment is not there, so that kind of quality control issues are there. So here we can see a brief economic growth of different types of fibers. So glass fiber is the most commonly used, and then there are different fibers, and we can see how the growth is increasing over the years. So all these units are in million tons here. The composite market is expanding at a very high rate, so we can see how it is rapidly expanding over time. So this was a very brief introduction of composites. We talked about the different types of composites, their constituents, properties of different constituents. We have seen the various properties of so based on the properties we have seen the advantages and relative advantages with respect to these constituents, and then we have seen how the various advantages or disadvantages of the composite itself, and then we have seen the broader market scenario of composites. With this, I would like to conclude this lecture here. Thank you.